Yes, I'm going to talk about formalizing soundness proofs of linear PCP SNARKs. This is work I did using the lean theorem prover. So first of all, what are SNARKs and why is it good to formalize them? Why are they good targets for formalization? So just what is a SNARK? It's this cryptographic primitive that's very useful for sort of compressing a proof that a particular computation had a particular result. So in a SNARK, we have a prover and a verifier. The prover has access to some program. In the case of the SNARKs that we're looking at here, it's a program that's represented in the form of an arithmetic circuit. And the prover might also have some private inputs to that circuit, and they can evaluate the circuit. And then what they can do is they can produce this proof pi that they can then send out, and that proof can then be received by a verifier. Verifier will also have access to the program or the circuit in this case. And they can receive this proof pi, and they should be able to check this proof against the output that the prover produced for the circuit, and they should be convinced that that output really does correspond to some particular inputs that were provided to the circuit. And the really key killer feature that SNARKs have is that the proof pi is of constant size, at least for the SNARKs that we're considering today. And this makes them very useful for applications, in blockchains in particular, but whenever you want a very compact proof. So the critical properties, cryptographically speaking, that the SNARKs need to satisfy, one of them is completeness. It should always be possible to create a proof if you're an honest prover. And there's also the zero knowledge property, which is commonly desired, which is that private inputs should stay private. But the property that we focus on in this work is really the soundness, which is that the prover should not be able to trick the verifier. Or put slightly differently, there should not be any adversarial prover that can come up with a proof which is faulty, but will be nevertheless accepted by the verifier. And soundness is a sort of very tricky property, really the trickiest of the three properties to prove, I would say, for a few reasons. There are sort of complicated mathematical justifications for the soundness, as we'll see. It's also important because there have been errors found in the past, in particular with the SNARK used for the Zcash cryptocurrency. It's also sort of tricky because, unlike other sort of settings, it's a setting where fuzzing won't help because you have a very large space of possible adversaries that you need to be able to defend against. And it's also just sort of philosophically important to do this, I think, because it's a composition of different types of computational proof. So applying formal methods to SNARKs is sort of unifying these two concepts of proof. And I think all of these reasons make SNARKs a pretty good target for formal security proof. So now I'll sort of describe the process that we went through to verify the soundness for these SNARKs. We ultimately verified 6 linear PCP SNARKs. The most well-known is probably Groth 16. So just a little bit of background about how a linear PCP SNARK is structured and the cryptographic model in which we prove them secure, which in our case was the algebraic group model. So for a linear PCP SNARK, the proof message is going to be made up of elements from some field, but in an encrypted form. They're going to be encrypted to these elliptic curve groups. And there are 3 groups in which the elements can be encrypted. There's the first group, there's the second group, and then there's this target group. And so the operations that you're sort of allowed to perform on these field elements that sort of hide within these cryptographic groups, well, of course, you can do the usual elliptic curve operations, right? You can add 2 elements that are in the same group, or you can multiply them by constants. But we also assume a sort of pairing-based model. So we assume that there's this efficiently computable elliptic curve pairing, which tells us that if we have one field element encrypted in the first group and a second field element encrypted in the second group, then we can do this operation to sort of multiply them and get a result that comes out encrypted in the target group. And so these are basically the three types of operations that you can do in this model. And it's sort of important to the cryptographic security of the scheme that you're not really allowed to do any other types of operations with these encrypted group field elements. So to walk through the steps of how a linear PCP SNARK protocol works, with an eye towards how we'll eventually go about automating proofs of soundness for these kinds of SNARKs. The first thing that happens is that there's a trusted third party that will sample some random field elements, and they will put these field elements, encrypted into the elliptic curve groups. At that point, the trusted third party will be done, and they'll ship this data that they produce, which is called the structured reference string. They'll ship this off to the prover and the verifier. Now it's up to the prover and the verifier to complete the SNARK protocol. So the prover will make some linear combinations of the structured reference string elements that they receive, and they will basically use this to create the proof pi. They'll send that to the verifier. The verifier can then do additional elliptic curve group operations and additionally pairing operations. And at the end of the day, the verifier is going to have to compare some values that they computed on the basis of these pairings, and they're going to have to check that they're equal. And if all of the checks ultimately pass, then the verifier will be satisfied that everything is above board and that the proof is a valid proof. And so an important thing to notice about all of the steps of this protocol is that at all times, the encrypted values that the prover and the verifier pass around, they always take the form of multivariable polynomials of the initial trusted third-party samples that were sampled in the very first step of the protocol. So basically, everything that is going to be computed on or moved between parties for the rest of the protocol from that point can be, in some sense, represented in terms of these multivariable polynomials. And the eventual upshot for this is that the statement of the soundness property for one of these SNARKs is going to take the form of a statement which says that some multivariable polynomial identities imply some other multivariable polynomial identity. And the nice thing about this is that this is the type of problem that is solved by a class of methods called Grosvenor basis methods. And so this sort of gives us a way into proving, in an automatic way that the SNARKs that we look at are sound. So just to do a quick walkthrough for a very simple SNARK, this isn't actually even technically a SNARK. Really, it's not even a complete cryptographic proof system, but hopefully it will nevertheless serve to give a basic demonstration of what one of these proofs look like. We have a SNARK that roughly computes this arithmetic circuit here. The structured reference string consists of these 4 random field elements that are encrypted to the 2 groups. The prover is supposed to return A alpha plus B beta in the first group, and the verifier is supposed to compute a pairing of that with C alpha plus D beta, and they're supposed to check that that is equal to E alpha beta. And then to show soundness, we have to show that this check implies this fact that either A times D equals E or B times C equals E. So the first step really is to load the assumptions and the goal into the proof assistant that you're working in, which in our case is lean. And so what we get in the case of this sort of toy SNARK is that we have this sort of polynomial equation with A prime, B prime, C, D, and E. And we have this sort of equality of polynomials that use these as coefficients. And we want to achieve this goal. This is basically what we want to prove within the proof assistant. So the first step that we can sort of take to do this is to sort of apply the distributive property of addition and multiplication. And this sort of normalizes the polynomial into this form where we have every sort of, the entire polynomial is basically a sum of different individual monomials. The next operation we can do is sort of compare like sides. So here we have for example, we have the alpha beta coefficient of the left-hand side of the polynomial is alpha prime times D plus beta prime times C. And the right-hand side, the coefficient of alpha beta is E. And that gives us this second equation here, which is basically just to say that if these 2 polynomials are equal, then their coefficients should be equal. And so that's basically allows us to sort of pop out of this polynomial form. And what we have now is sort of a sequence of recursive casework and simplification that helps us sort of simplify the problem a lot. So what we have here, you'll notice, is that A prime times C equals 0. That's an equation that we have. And we can case on that to split it into 2 sort of disjuncts. Either A prime has got to be equal to 0 or C has got to be equal to 0. And once we have that, we can do this case work. We can say, okay, in case 1, we'll assume that A prime is 0, and in case 2, we'll assume that C equals 0. And we can use these statements to simplify the rest of the term. So we can replace A prime with 0 wherever we see it on the left-hand side. We can replace C with 0 wherever we see it on the right-hand side. We can simplify terms away. And eventually we'll get to a point where all of the cases that we're dealing with have one sort of equation in the hypotheses which is enough to satisfy our goal. So in this case, we have B prime times E equals E on the left-hand side, and that's enough to sort of satisfy the goal. And the same with the right-hand side. So just to sort of summarize the totality of the work we did, we summarized 6 different SNARKs. We summarized some of the early SNARKs from the literature, including the GGPR SNARK and the Pinocchio SNARK. We also then basically satisfied several variants of the Groth 16 SNARK. There's a type 3 version that uses basically type 3 pairings. There's sort of different restrictions on what can be done between the first and second elliptic curves. But basically, it was sort of fairly, once the first of these fell, it was rather, well, I don't want to say easy, but it was relatively easy to do the rest. Some of them took longer than others. In particular, the Groth 16 itself took much longer to actually complete the computer checking of the proof because there was actually quite a bit of casework in the analysis for that SNARK. And there are some additional complications. I've sort of, in the previous example we saw, we had this sort of simple A, but really these are sort of formal sums of terms. That doesn't really affect the proof too much. And another sort of complicating factor is that instead of polynomials, these are actually Laurent polynomials. It's technically permissible to have negative exponents in these polynomials, but this also doesn't affect things too much. And just another sort of challenge that has to do with this is the sort of fragility of the underlying proof system, because Lean is really a project that's still under active development, and it's basically switched from Lean 3 to Lean 4 during the time that this project was completed, and keeping things up to date is sort of another sort of challenge working with this sort of code base. But yeah, so thanks for listening to the talk. You can see the code here at this GitHub repository.